presenting problem number 1, 2D foam. So the problem states, soap foam enclosed between two glass sheets appears as a network of polygons. Such foams evolve with time as individual bubbles move and coalesce, and the liquid drains out. Investigate the structure and evolution of 2D foams. So if we look at the phenomenon, we see here we have a plate of, as it states in the problem, soap foam. And in my case, in the phenomenon, first it is a network of soap bubbles, which would then evolve into a network of polygons. Then in the second part of the task, it states that the bubbles move and coalesce. And as you see in this video, you can see that the bubbles are moving slightly upwards, and we also see that bubbles are coalescing, which I will explain later. And it also states that we have to look at 2D foams, and this is an example for a 2D foam. So what is a soap foam? So soap foam, we have a liquid, and we put in soap, and then we mix in a gas so we get our bubbles. So the soap is in a fluid, which means that the bubbles and the liquid will move. Now, if we look more exactly at a soap bubble, we have our soap molecule, which has a non-polar tail and a polar head, and it decreases the water surface tension, and it will also trap the water in a layer. So if we look at the soap bubble, we have our water layer in green, and we have the soap bilayer layers, which are made up of those soap molecules around the water layer. These together are called a soap foam. If we look at this as a 3D shape, which we would see if we just had it in air, it would be a sphere because that is the smallest surface for the given volume. Now we are looking at a 2D shape, so it would be a circle, which would be the smallest perimeter for the given area. So if we look at the properties of pressure, we have our soap bubble again with gas inside and the soap foam, and the next bubble would start outside, that's why there is gas there. So the soap foam has a surface tension, which puts pressure on the gas inside, and there's also pressure from outside, from the other bubbles, and there is a pressure from inside. Because the bubble size is only stable if the pressure from inside equals the pressure from outside plus the pressure of the soap foam. If we look at this compared from a smaller bubble compared to a larger bubble, we have the pressure of the soap foam is larger in the smaller bubble than in the larger bubble, which means that the pressure inside the bubble has to be larger in the smaller bubble than in the larger bubble, because if the pressure from the inside would be smaller, the bubble would collapse, and if it were bigger, the bubble would burst. These arrows, of course, are just a demonstration. Of course, the pressure is applied all around the circular shape. So if we look at bubble collision, we have a small bubble and a medium bubble, and so the pressure in the small bubble is larger than the pressure in the medium bubble, which means that the small bubble will press into the medium bubble, and so we have a curved border where gas can go through, and this is called coarsening when bubbles exchange gas. Now, then we have a large bubble finally, they should merge, and that is called coalescence when the bubbles merge. Now, if two same-sized bubbles collide, they will form a straight border, and if we look at many bubbles, we have the borders that turn into lines, and the circles which turn into polygons. Now, what is a polygon? So, we have a polygon, which is a two-dimensional shape, and it is a closed figure, and it has straight line segments. This is a regular polygon, and in regular polygons, all the sides and all the angles are the same. This is a regular hexagon. So if we look at this as a network of polygons, if we look at, for example, a network of regular hexagons, this is what it would look like. Now, it states in the problem that we have drainage of liquid. So what does that mean? So we have a 3D foam between two glass sheets, which would look something like this. And as it states, we need glass sheets. And this is a quasi-2D foam. Now, because of gravity, the space between the two glass sheets will decrease. And so the liquid will drain out and the bubbles will coalesce. With all that theory, we can look at my hypotheses. So for my first hypothesis for coalescence and coarsening, I believe that the smaller bubbles will push into the larger bubbles and will also coalesce into the larger bubbles, which means they will disappear. For my second hypothesis for the evolution, I believe that over time, the network of soap bubbles will approach a network of regular hexagons. And for my third hypothesis, I believe that for the soap foam mixture, if we add too much soap to the mixture, no liquid will drain, no bubbles will coalesce, and no polygons will appear. So for my experiments, for my parameters, I looked at different liquid mixtures, and I looked at different amount of time. For my control, I always had the same type of soap. How I created the foam was always the same, and I always used the same glass sheets. And for my variables, I observed with the bubbles, I observed the number of bubbles, the size of the bubbles, the curvature of the bubbles, and also the angles where the bubbles met. For my materials, I used distilled water, tape, an air pump, glass sheets, rubbing alcohol, cups, gloves, liquid soap, whisk, measuring cup, and paper towels. Then for my procedure, I made the soap foam mixture, and I created bubbles with my air pump. Then I drained the liquid, and I cleaned the glass sheets with rubbing alcohol. Then I put the foam onto the glass sheets and put the other glass sheet on top. For my setup, I had a black box for a dark background so we could clearly distinguish where one bubble ends and the next one starts. And I have a tray with a phone for a camera so I could take nice videos and pictures which you can observe later. And I had, of course, my glass sheets with the foam on it as the problem states. For my results for bubble collision, we have this picture here, and as you can clearly see, all the smaller bubbles curve into the bigger bubble. And I want to focus on these 5 points. So after 150 seconds, we can clearly see that all the green bubbles diffuse into the bubbles around them, which means there was coalescence happening because all the bubbles disappeared, and also the pinker bubbles shrank, which means there was coarsening happening. So for my results for coalescence and bubble size, I have these two pictures. As you can clearly see, after 15 minutes there were fewer small bubbles and the largest bubble grew, which again shows that there is coalescence happening. And then for my results for angles and hexagons, again here you have a picture and then we have a picture after 35 seconds. If we look at these pictures next to each other, I want to focus on these 2 points. And so first here we have 4 bubbles that met and then 3 bubbles that met, and because they should approach a form of a regular hexagon, always 3 bubbles should meet, so they always have the angle of 120 degrees, which would form a complete circle. In this case, we also have first 4 bubbles that meet and then 3 bubbles that meet. Also, I want to mention that this polygon became more regular, which means it approaches the shape of a regular hexagon more than it did before. Now for my results for different soap foam mixtures, I have the liquid soap, which is 15% soap and 85% water. Then I have this picture after 15 minutes with 10% liquid soap and 90% water. And if you observe my pictures before closely, you can see that there are clearly less smaller bubbles than in the other pictures which were taken at 0 seconds. And here we have 100% liquid soap, and as you can see, all the circular shapes remained, so there was no evolution at all. For my conclusions, for my first conclusion to coalescence and coarsening, I clearly saw that the borders curved, and I also saw disappearance of small bubbles, which shows that there were coalescence and coarsening happening. For my second conclusion to the evolution, I clearly saw that 3 bubbles met. There were also a lot of polygons, and were a bunch of regular shapes. They might not be a complete regular hexagon, but because we observe them with our eyes, they look like a regular hexagon. And for my third conclusion for the soap foam mixture, I saw that if we used too much soap, no polygons appeared and there was no evolution. Here are my references. Thank you for your attention.
Okay, thank you very much. Clarifying questions from the opponent, please.
So he only investigates the evolution over the 15 minutes he showed.
No, I used different durations of time, so I had some experiments that were
What was the largest one?
15 minutes. I showed 15 minutes, but the largest duration I used was 1 hour.
And did you present any of it on the presentation?
The 1 hour ones?
Yes.
No, I showed, the results I showed were the ones that were the most clear to explain what happened in the evolution.
How did you space out the glass plates? How do you space them out so they don't just stick here? Do you have any spacing between them?
I couldn't measure the spacing because it was so close, but of course they still have a difference between them.
Okay, and can you make sure that this is constant? Yes or no?
I can't completely make that as constant, but I think because I always use the same glass sheet, it is as constant as it can possibly be.
Okay. Do you think there are any quantitative parameters that you could vary?
You could definitely, if you have some kind of program to track bubble evolution, you could have done that, but those materials were not available to me, so I think qualitative results are enough to explain this problem that I solved.
Okay, so how does the foam drain out? Does it drain out?
The foam, because the glass sheets, the space decreases, the liquid is the thing that will mostly drain out, but of course also some of the foam drains out too.
Okay, and how do you define 2D foam?
I define 2D foam as, well, it is on a surface, so which means between the glass sheets it is not complete 2D foam, it is quasi 2D foam, which is still kind of like 3D foam, but on the surface if we just observe the surface, it is still 2D foam.
So do you have any rigorous definition that that defines a 2D foam apart from a 3D foam?
We would have to observe a flat foam, which is practically impossible, and also, but if we, exactly as I said, observe only the surface, it is counted as a 2D foam.
Okay, you spoke about the pressure of the smaller bubbles always being larger than the pressure of the bigger ones.
Yes.
Is this always the case?
Yes.
And can you prove that? Yes or no?
Well, first of all, I can prove it with my experiments, as you saw.
Okay. Okay, so thank you. How exactly do you define 2D foam, because it was not clear from clarifying questions. And does the foam depend in any way on the type of soap used? Because you only used one type of foam, I believe. I also did not see any variation of how much liquid you used for making of the foam, and I would like to discuss that. So yeah, I believe we should start discussion now.
Okay, before that, let's thank the opponent for the and we proceed to the discussion between the reporter and the opponent.
Okay, so what could quantify the evolution of the foam?
You could definitely write a program to track the foams or see how many foams first had four bubbles met and then 3 bubbles, which I did, but I did not see any different results in that one. So I showed the qualitative one because there's more to visualize. And I believe you also criticized that I only showed one big bubble with the curves. I chose that place. Of course, it happened in all the other experiments too, but I showed that place I showed that spot to explain what happened in all of the whole experiment.
You did not prove a point that was not obvious. I mean, you just showed the curved surfaces and then you did not make any point on it. Can you connect to the representative right away?
So I believe you meant
Yep. These bubbles. What point do you actually make from these? Because I don't see anything that was not really obvious about the structure of the foam.
Well, I believe that when I show my results, why I showed this spot is because here you can see very clearly that all the small bubbles curve into the larger
This one
bubble.
does not.
Well, that must mean that it definitely is curving a bit, or it must be the same size. As I explained in my theory, if two same size
By the
bubbles
way,
approach each other, they form
how do
straight
you
borders.
define same size? Is it a linear size or what?
The same size, that would mean the same area.
Same area. And since you didn't space out the glass sheets, could you at least say what kind of spacing they had? Just an order of magnitude.
Because we put one glass sheet on the other, we cannot see the spacing with our visible eye. But of course, there is some space in between.
Yeah,
as
but
I
it's not
mentioned.
constant. Because if they are being on top of one another, there is at least one point at which they touch. Because otherwise, they won't be on top of one another. They would be separated.
Yes, they are separated just a tiny bit, of course, because the foam is in
But it's not
between.
constant.
Well, I use the same glass sheets at the same time, but of course there is some error in it. But I try, because I use the same glass sheets all the time, it would be as constant as it possibly can
it
be.
would not be constant around the foam. It would be constant for different experiments, but not around the foam. So for example, if there is a bubble here, it might show different properties to the one here. Okay, do you think you could have spaced the glass sheets in any way?
I'm not sure how you would mean spacing the glass sheets.
Okay, so here is a suggestion for you. I would suggest using, for example, even you can use paper to space out glass sheets, and that would be a very good addition to your experiment.
But how would you space out the glass
You just
sheets?
place paper on the edges. Okay, let's
But
continue.
that wouldn't. If you would space out the 2D foam, that would mean that you have less constant 2D foam. That means you would
Yes.
have less 2D foam and more 3D foam. Because
no,
if
2D
there's
foam-
space between them, it would still be 3D foam.
No, 2D foam is by its definition not foam which is very short, and it's foam that is rather does not have one bubble on top of another bubble. So
I don't have one bubble on top of the other bubble.
that is okay. Okay. However, the goal of this experiment is not to make the foam as narrow as possible, as short as possible.
I don't think that was the goal. I just
Yes.
think that it states that we need to use 2D foam. So
Yes.
I tried to make
That is correct.
I tried to make 2D foam, but of course there
Okay,
is some
let's
error.
go to the next question. How could you quantify the structure of the foam if you couldn't quantify the evolution of it?
You could pretty much count every bubble if you have some kind of tracking device, and then compare it to like after 1 hour or something.
What would you compare exactly?
Maybe how many bubbles there are, or how many meeting points there are, or how many straight borders there are.
Just the number of bubbles and this kind of stuff. Okay. So I would suggest here that you rather look at the size distribution of the bubbles, and I think that would be a relevant parameter.
Well, of course you can use a size distribution.
Okay, let's go to the next question. Do you think that the amount of liquid you used for the foam actually affects it?
Of course it does, because if you use too much soap, there won't be that much of a pronounced evolution, as I showed in one of my
However, did you investigate anything in the middle of these?
Okay, we're out of time, so let's thank the reporter and the opponent for the discussion. Clarifying questions from the reviewer, please.
Hello, I'm a reviewer from Team Georgia. First, I'm going to ask the reporter, did you actually measure any parameters experimentally? Like the curvature or...
Well, I observed the curvature, because measuring the curvature would include a lot of different programming.
So you have not measured?
Well, I observed it.
And which parameters have you measured, not only observed?
Well, I definitely measured at one point how many bubbles first met, 4 bubbles met, and then 3 bubbles met.
Okay.
And
how did you get the foam itself? Making process.
So I made my soap foam mixture with, and then I used an air pump to create the foam, so it would be as constant as possible.
And was the distance, I have to repeat this question to be more clarifying, was the distance between glass sheets constant?
Well, I always use the same amount of glass sheets, so they were as constant as they possibly
But
can
how
be.
did you control the distance between two glass?
I couldn't see them with my naked eye, so I couldn't really keep them exactly constant, but they were as constant as they could be.
Clear. I want to ask the opponent, how would it affect the evolution of the bubbles?
Which one?
In the report, the distance between glass sheets was not fixed.
Well, I believe that in the way she did the experiment, by just placing the glass sheets on top of one another, you have to have at least a few points where the glass sheets actually touch. So there you could not have any, and in these points and the surroundings of them, you could not just have a fault.
And the final question, does the bubble area change over time, for both? First, reporter.
Excuse me, can you?
Does the bubble area change over time?
Well, the bubble evolution, the shape of the bubble definitely changes over time.
What does the opponent think?
The shape distribution, that is the relative number of bubbles.
Yes or no? Does the area change?
No, it does not change.
No, it does not change.
Thank you.
Overall, it does not change.
Okay, thank you for the questions. Now we have your preparation
So review problem number 1, 2D foam. Let's revise the problem, but I'm going to just point out most important word. In the report, there had to be investigated the structure of 2D foam, among liquids that drained out, also the polygons and other parameters which were very important for the report. And now I'm going to outline the report itself. I think the problem interpretation and definition was actually great, and the job was really well done. But the theory about gas exchange between bubbles was not enough for me, because I really wanted to see how the particles would pass between the layers on a microscopic level. Also, the parameters such as number, size, curvature, and angle were not observed, were not measured experimentally, and the theory did not evaluate the angle between fields and curvature of the field, which is very important. By the way, I think that the experimental setup was really cool, and we we were able to observe the whole process of bubble exchanging and see the dynamics of this problem. But the thing that reporter had not fixed the distance between glass sheets was really messed the whole experiment. And finally, I think the analysis was not good because there was no comparison between theory and experiment, but the conclusion was average. These are the strengths and weaknesses of a reporter. I think that the impressive experimental set of examples of coalescence was an amazing for the report, and she also explained why small bubbles unite with big bubbles, and this was very clear, and also very two types of soap, which is also an advantage. However, in the report, she did not measure distance between glass sheets, and for this reason the glass crushes actually the foam, and we get another parameter which we don't know, and this fully changed the problem itself. And also she did not define 2D foam very well, and sometimes it was exchanged to 3D foam and didn't explain how glass sheets were fixed, and did not measure the fastness of coalescing bubbles. These are the strengths and weaknesses of the opposition. In the quick questions asked about measurement distance between glass sheets, which was very quirky and impressive, and notice that Chi's explanation was only qualitative and not quantitative, but he wrongly answered my question about bubble area. This bubble area really changed over time because of unition of big bubbles to small bubbles to big bubbles. This means that bubble area definitely changed, and the amount of films too. And in the discussion topics, opponent asked about large distance between glass sheets, and reporter said that foam would become 3D, and we agree with the opponent. Thank you for your attention.